Welcome back, everybody. This is the first of two sections where we talk about how to make new functions out of functions we already have. In this section, we'll look at how to combine functions using addition, subtraction, multiplication, and division, and then also something called function composition, or composition of functions, which is the title of the section. So let's get started. Section 1.4 is about several topics, one of which the title topic is composition of functions. But actually, the first thing is to look at what's called the algebra of functions. And so basically, let's start by saying let's let f and g be functions, and let's let f's domain be A, and the domain of g is going to be B. Then we can form the new functions called the sum, difference, product, and quotient functions, basically just as you would expect. We're going to add, subtract, multiply, or divide the two functions. There's kind of a special notation for it. We have f plus g of x and f minus g of x and so on. Notice here we're not multiplying by x. It's just we're creating a new function that is has its name f plus g of x. For the domains, it's going to be the intersection of the existing domain. So if we combine our functions f and g to create a new function, f plus g, the domain will be the intersection of the existing domains. For division, we have to additionally be careful to make sure that we're not dividing by 0. So this thing that looks like an E, by the way, that stands for element of. So this says x is an element of the intersection of A and B, which we had already, and additionally, we need g of x to not be 0. So you could think of the domains as basically the domains that we would need in order to have a real number output. Okay, so let's see an example. So here we have two functions. F is going to be 3 minus x squared. G will be x minus 4. We're to find f plus g, f minus g, f times g, and f divided by g along with their domains. So let's go with f plus g first. F plus g of x, that will be just as you expect. It's 3 minus x squared plus x minus 4. And then it would be nice to go ahead and rewrite the terms so that they're in standard form. So we'll say minus x squared plus x minus 3. And then for the domain here is not too bad. For f and g both, the domain is all real numbers. So the domain is going to be on all three of the first parts, sum, difference, and product. At least it's going to be all real numbers. Okay, for the difference, f minus g of x will take 3 minus x squared minus x minus 4. Okay, and so then as before, we're going to combine like terms and then put down the domain. So we'll have minus x squared, this time minus x, and then plus 7. It'll be the same domain as before. For the product, f times g of x, we're going to multiply the two together. We'll have 3 minus x squared times x minus 4. Okay, and so we should go ahead and also multiply that out as well. So we'll have a degree 3 term, that's minus x cubed. And then we'll have plus 4x squared. And then we'll have an x term of 3x. And then a constant term looks like will be negative 12. And the domain, again, is going to be all real numbers. It's going to get a little bit more interesting with the division. Here we have f divided by g of x. This will be 3 minus x squared. We're dividing by x minus 4 for our quotient. Now here it's gotten more interesting because the domain is no longer all real numbers because we can't allow x to be 4. So in interval notation, it will be negative infinity up to 4, union 4 to infinity. All right, so sum, difference, product, and quotient. All right, so another example. Here we have a different f and g, of course. So f will be the square root of x minus 2. G will be 1 over x minus 4. So first of all, let's note f's domain. Okay, we have a square root here. We always want to make sure we're taking the square root of a non-negative number. So we need x to be at least 2. So it will be 2 to infinity. For g, again, we can't let x be 4. So it will be, let me use set builder notation this time because it's a little bit shorter to write. So the set of all x such that x is not 4. For the sum, we'll have, just as you would expect, the square root of x minus 2 plus 1 over x minus 4. And then we're going to have to think about the domain for that. So f required x to be at least 2. For f, it's defined at 4. G is defined for some negative numbers, just not 4. But we need the intersection of the two domains because we need basically the two parts to have output as defined as real numbers. So a way I like to think of this is to think about the number line. We'll start with everything, that is all real numbers, and then we're going to throw out the stuff that's not going to work. So in order for f to be okay, we need to have just 2 to infinity, right? So we'll take all the numbers to the left of 2 and throw those out. Okay, so just 2 to infinity for f's sake. But then g requires us to not have 4. So we're going to punch a little hole in here at 4. Then the domain will be from 2 up to 4. And then we'll have a round parenthesis because the 4 itself is not included. And then from 4 up to infinity. So that will be the domain on our sum function. All right, so now we're going to do f divided by g of x. So we'll have the square root of x minus 2. It's divided by 1 over x minus 4. And then, as you know, dividing by a fraction, we're going to multiply by the reciprocal. So we'll have the square root of x minus 2 multiplied by x minus 4. I like to write that with the x minus 4 in front. It just looks nicer to me. This x minus 4 times the square root of x minus 2. For this one, we have to be a little careful about the domain. On the face of it, it looks like, well, yeah, we just need to make sure that the x is at least 2. And it doesn't look like there's any problem with the 4. But the thing is that since we're combining functions f and g, g already, as soon as that enters the picture, that means we need to not be using 4 for an x because it's not in the domain of g. And so even though it looks like we're no longer dividing by x minus 4, the 4 is already gone as soon as our g was involved in the problem. And so the domain here is going to still be from 2 to 4 and then 4 to infinity, not including the 4. All right, so this has been a quick look at how to combine functions using addition, subtraction, multiplication, and division. We're going to go on to looking at function composition next. So the second way we have of making a new function from existing functions is by doing what's called function composition. And if you think about how the word works, composition is a putting together of things. And so, yeah, sure enough, we're putting together functions. We were doing that before, but this is a putting together of functions in a special way. So definition first, and then some examples. Given two functions, f and g, the composite function, f circle g, also called the composition of f and g, is defined in the following way. We have f, a little circle, and then a g of x, and it's f of g of x. So what we're doing is we're taking the function f and we're giving it g as input, okay? Notice here this is in fact a little circle. It's not the same as the times dot, okay? That's different. This is f, a little circle, and then a g. And it means the composition of f with g. We're taking our function f and we're giving it g as input. You'll notice that the order of the functions makes a difference. Here on the left side, the g is closer to the x and the f is on the left side. Here we have f on the left side, and again, the g is closer to the x. So the order that those functions are in is going to be consistent all the way across. All right, so there's a little symbol for this, or a little graphics for this. If we have a value of x, we'll be giving that as input to g. So x will be given as input to g, giving us a number g of x. That number g of x, we're going to turn around and put into f, giving us f of g of x. That function that does those two steps is f circle g of x. Okay, so let's see some examples just of evaluating functions, and then we'll see function composition. Okay, so here, just a little review. Let's let f of x be the function 2x plus 1. We're going to find f of 3, f of negative 4, and then a couple of others. So for f of 3, that will be 2 times 3 plus 1, or 7. F of negative 4 will be 2 times negative 4 plus 1. That's negative 8 plus 1, which is negative 7. That's kind of cute. Here we're putting k into f. What's k? Doesn't matter. F doesn't care. F says, whatever you give me, I'm going to double it and add 1. Okay? So f of k will be 2k plus 1. Okay? And that's it. That's all there is to that. For f of x plus h, we did this a little bit with the difference quotient, right? Here, f of x plus h is 2x plus h plus 1. And here it's polite to go ahead and get rid of those parentheses. So we'll get 2x plus 2h plus 1 in the end. So the big idea here is that we can plug in numbers into functions, of course, but we can also plug in variables or other expressions. And that's the basis for how that function composition is going to work. We're going to put a function inside of another function. All right, so let's go ahead and try that. Let's let f of x be 6x minus 5, and g of x will be the square root of x. We're going to find f circle g of x and g circle f of x. So let's try. F circle g of x, that means we're finding f of g of x. Okay, but what's g of x? G of x is the square root function. So we're finding f of square root x, because that's what g of x is, it's the square root. We're going to take that and put it into f. F says, whatever you give me, we're going to do 6 times that, take away 5. So 6 square root x minus 5. Okay, and that's it. Let's go ahead and try g circle f of x. You might want to pause the video here and try it on your own. Okay, so let's see how g circle f of x works out. That will be g of f of x. This time we're taking g and we're putting f into it. So f is the 6x minus 5 function. And so we're putting that into our g. G was the square root of x. So we have the square root of 6x minus 5. Those two are different, right? So this example illustrates that in general, g of x or g of f of x is not necessarily f of g of x, right? You could say that function composition is not commutative, if you like. Okay, so a couple of examples where we've formed the composition of two functions. Okay, in the last example, we found compositions using formulas. We can just as well find compositions using functions values given in a table. So here I have a table of values, and we're going to calculate first f circle g of 0. This will be f of g of 0. So let's take a look at the table for g of 0. X across the top, when x is 0, if you put that into g, you'll get 1 out. So we have f of 1. Now we're going to put 1 into f. If you put 1 into f, you'll get an output of 3. So the final answer there is going to be 3. Let's try that again. We want g circle f of 3. This will be g of f of 3. We're going to take an x value of 3. We're going to put that into f. An x value of 3. We're going to put that into f. We'll get -1. We have g of -1. Where's -1? An input of -1, we're going to put that into g and get 0 out. Make sure that you can see where each of these is coming from. And if you can't, let me know. F, circle f of 2. So here we're taking f and putting it into itself. This will be f of 2. So f of 2. An x value of 2, we're going to put that into f, and we'll get 1. F of 1. We saw in example A that f of 1 was 3, so we'll get 3. Here we did function composition where the function values are given in a table. In our next example, we'll do the same basic thing, but this time our function values are given in a graph. So we have a graph of a function g shown in blue, that's on the upper left, and a function f in red that is kind of on the right. We're going to do at least the 3 highlighted ones, and so let's see what we've got. We want g circle f of 4. This will be number 35. We want g of f of 4. So we need to take an x value of 4 and put that into f. Here, x value of 4, if we put that into f, the y value is 2. That means that we're finding g of 2. So now we have an input of 2 that we're going to substitute into g. An input of 2 substituted into g will give us 5 for an output. So g of f of 4 is going to be 5. Let's try 2 more. So number 34, we have g of f of 0. So we're going to put 0 into f. We'll get 0 out. We're going to put 0 into g. If you put 0 into g, you get 3 out. Okay, next up, number 38. We're going to find f of 4. So we're going to take an x value of 4 and put it into f. That will give us 2. We're finding now f of 2. Our input value of 2 will give us in f an output of -2. In these 3 examples, we were finding function compositions where the functions were given in the form of a graph. In some of these examples, it can really seem like we're just playing around. Like, let's take this number, put it into this function, and then put that into some other function. It can seem like we're just playing around, and you wonder what application this could have. Here's one example of an application. It is a little bit contrived, but it will give some sense of exactly how this is going to work realistically. So here the story is: a stone is dropped in a lake, creating a circular ripple that spreads outward at the speed of 60 centimeters per second. For part A, we're to find a function g that models the radius of the radius as a function of time. So g will take time as input and give the radius as output. So this will be part A. So that means we could think about this by thinking about a couple of values. Well, at the instant the pebble hits the water, that is at time 0, the radius should be 0. Okay? The ripple travels outward at the speed of 60 centimeters per second. So that means after 1 second, the radius should be 60 centimeters, right? After another second, it should be 60 plus 60 or 120. After another second, it should be 60, 60, and 60 or 180, right? If t seconds go by then, well, we're multiplying 60 by the number of seconds it is. So it'll be 60t. So that means our g of t is going to be 60t. That's our answer to part A. The input is the time in seconds. The output is the radius in centimeters. Okay, next up, we want to find a function f that models the area of the circle as a function of its radius. This will be easier. So you know the area for a circle. Area as a function of radius, area is pi r squared. Okay, and that's the end of that. For part C, we're to find f circle G. So I guess here we should have had, instead of calling that A, I should have called that F. Okay, so f of r. All right, so we want to find f circle G of T. So this means we're finding f of G of T, and we're supposed to tell what this represents. So we're taking f, which is this pi r squared function, and we're putting into it G of T. So this will be pi G of T squared. That will be pi times 60t squared. And then doing the arithmetic, you should have 3,600 pi t squared. Okay, and that's our function. Okay, so what, right? What this represents is the area as a function of time. So normally we think of area, okay, area of a circle, pi r squared. Okay, the area of a circle depends on what the radius is. But the thing is here is that the radius itself depends on time. So we can kind of skip the middleman and say, okay, well, how does the area depend on time? And it's through this function composition, basically. We were able to kind of skip over that g function and go straight to saying, okay, well, if the input is t, what is going to be the output area? Like I said, it's a little contrived, but it does give a sense or feel for how composition can be used. One more application. So let's take a look. So here it says, let's say that you have a $50 coupon from the manufacturer that is good for the purchase of a cell phone. The store where you're purchasing the phone is offering a 20% discount on all phones. Let X represent the regular price of the phone. Part A, suppose only the 20% discount applies. Find a function f that models the purchase price of the phone as a function of the regular price x. So we want the sale price as a function of the regular price if you get a 20% discount. So let's think about that. So we want f, that will be f of x. It will be the regular price, that's x, minus 20% of x. We're taking 20% of the regular price away from the regular price. So this will give us x minus 0.20x is 0.80x, right? So another way of thinking of that is that if you're taking 20% off, that means you're paying 80% of what the regular price was. So that will be our f. F of x is going to be 0.80x. Okay. If you didn't quite get how I got the 0.80x, remember that this x up here, that is the same as 1x, right? So we could look at this as 1x minus 0.20x, and then factor out the x, right? If you do that, you'll have 1 minus 0.20 times x. That's where I'm getting that 0.80 from, okay? All right, so now, instead, let's suppose that only the $50 coupon applies. You don't get the 20% off anymore, but you do get the $50 coupon. This will be easier. So our g of x will be the regular price minus $50 using the coupon. Okay. So now for part C, if you can use the coupon and the discount, let's say they say sure, okay, you can use the coupon and you get the 20% off. Depending on how they ring it up, you're going to get one of two different prices, either f circle g of x or g circle f of x, depending on the order in which they apply the two discounts. So we're going to calculate both of these and decide which gives the better price. So let's first find f, circle g of x. This will be f of g of x. Here we're taking our function f and we're putting in g, f x minus 50. F was 0.80x. So 0.80 times the input, x minus 50. And then let's go ahead and distribute to remove the parentheses. So that will give you 0.80x. And then 0.8 times 50 will give you 40. Okay. That's the first composition. Now we will have g circle f of x. This will be g of f of x. This time we're taking g and we're going to put f into it. So g is our take away 50 function. We're going to have this, yeah. 0.80x is our input. And so we'll have 0.80x minus 50. Okay, so then it says which one gives the lower price? Well, 0.80x minus 40 or minus 50, the second one is lower. Okay, so let's think about that in the context of the story a little bit. So you have this phone, the regular price on its X. They can either take $50 off or they can take a percentage off. If you think about it, you're better off if they do the percent discount before they do the flat dollar amount of discount. If they're lowering the selling price of the phone by $50, then you're paying that 20% savings is off of a smaller amount, which is why you're better off doing the 20% off first and then the $50 off after. All right, so this example also a little bit on the contrived side, but also does illustrate the difference between the orders on two compositions. We just have one more slide and then we're done. Okay, one of the tasks that we do in calculus, and is also kind of interesting, is going the other direction from forming a function composition. And that would be, instead of saying, okay, well, we have these two functions, we want to put them together and see what we get. Instead, let's take a function that we already have and see if we can break it into two functions whose composition is given. So here in A, we have an h of x that is 2x plus 1 raised to the 7th power. And we want to try to rewrite this in terms of an outer function, f of x, and an inner function, g of x. So taking a look at it, we can look at this as an outer function that says, okay, let's raise whatever to the 7th power. And our inner function will be 2x plus 1. So g of x could be 2x plus 1. And then our outer function, f of x, is whatever you give me, we'll raise it to the 7th power. The thing about doing this, though, is that it's not unique. There's only one way of doing it. There's not only one way of doing it. We could just as well have said, well, let's let the inner function be add 1 and then 7th power. So that will be our inner function. Add 1. And then our outer function, could be, I have those backwards. Let's do the inner function as, I'm used to doing it this way because this is really the right way, kind of. We'll do it as the inner function, just times 2. And then the outer function will be add 1 and then raised to the 7th power. Okay. This first way is more desirable. Basically, the reason why you would really learn this is for a particular procedure that you would follow in a calculus class. And there's a certain way of doing it that works best in that context. So that's why we look at it right here. H of x is 1 over 3x plus 1. We want to kind of think of this as in terms of an inside function, which will be our 3x plus 1 here. And then here our outer function will be the reciprocal 1 over x. You want to take a look at these and make sure that you can see how forming those compositions would give you the given h of x. Okay, so I'm sure one of you has already thought, well, how about if I just make g of x be x, and then the f of x would be 1 over 3x plus 1. And sure enough, yes, that would also do it. That's actually going to give us a function whose composition is h of x. But like I said, for the task that you would truly want to perform in like a calculus class, you would be trying to break down a more complicated function into simpler functions. And this middle one is not going to be very helpful in that regard. One that would be kind of in the middle as far as helpfulness goes would be to have our inner function be just the 3x, and then the outer function would be 1 over x plus 1. I'll leave it to you to check that this composition of f circle g is going to give the same h of x. Okay, last example, you should pause the video and try this one on your own. See if you can come up with a couple of different ways of breaking up our h of x that will give us what it is that we want. So here, our outer function will be a square root. We could have as our inner function 2x minus 9. That's going to be the simplest. We could also have as an inner function our doublet function, and then as an outer function square root of x minus 9. All right, so this takes us to the end of the section. Let me know if you have any questions, and then have a great day.